The zipper quietly changed the way garments, bags, and many other objects close and open. Its story begins with simple needs for fastening that did not come from a single invention, but from many small attempts over time. Early fasteners were often cumbersome and required separate parts or complex stitching. The idea of teeth meshing together and a device to guide them into alignment emerged slowly. Patents and prototypes multiplied during the late 19th and early 20th centuries as inventors sought reliable solutions. Some of those early machines were intended for shoes, others for clothing, and some for specialized equipment. The gradual refinement of the zipper involved improvements to the teeth, the slider, and the fabric tapes that hold the assembly. Manufacturing methods evolved alongside the design, allowing zippers to be produced at scale. The following sections examine how particular changes in form and material shaped the device we use today. Each development tended to focus on simplicity, reliability, and the needs of manufacturers and consumers. Over decades, the zipper moved from novelty to near ubiquity in everyday life. Before zippers became common, people used buttons, hooks, laces, and toggles to secure openings. These earlier fasteners often required manual dexterity and took time to operate. Some designs attempted to speed the process with sliding components or interlocking edges. Narrow strips of metal or fabric were sometimes sewn together in patterns that hinted at later zipper teeth. Tailors and shoemakers experimented with devices that could close seams more efficiently than ordinary stitching. Many of these experiments were local and practical, made to solve a specific problem rather than to become a general product. As mass production and ready-made clothing developed, the demand for faster, more consistent fastening solutions increased. The context of industrialization encouraged inventors to file patents and collaborate with manufacturers. These modest beginnings set the stage for gradual technical convergence toward a single, repeatable mechanism that could be produced at scale. The transition from bespoke fasteners to a standardized component took several decades and many small steps. One early commercial attempt at a slide fastener came from an American inventor who sought to streamline shoe closures and garment openings. This design introduced the concept of a continuous chain that could be engaged and disengaged by a sliding element. The initial versions were imperfect, prone to jamming and separation under stress. Inventors improved the guides and the alignment of the teeth to reduce these failures. The early commercial machines produced parts that varied in precision, which affected their acceptance by garment makers. Production techniques at the time limited the fineness of the tooth profiles and the consistency of the tapes. Despite these limitations, the idea gained enough attention to attract further investment and experimentation. Designers focused on making the slider more reliable and the teeth easier to align. Over time, improvements in stamping and machining allowed better fits between parts. This phase laid important groundwork for the more successful designs that followed. A significant refinement of the fastener came with improvements to tooth shape and attachment methods. A more effective tooth profile allowed parts to mesh securely while remaining easy to separate when needed. The slider mechanism was redesigned to guide teeth into a precise track, improving alignment and reducing strain on the fabric tape. Attachment methods were changed from crude rivets to more secure anchoring that distributed forces along the tape. The combined effect reduced failures at high use and made the device suitable for a broader range of materials. Manufacturers adopted the redesign because it reduced returns and complaints and allowed for higher production volumes. Materials science of the period contributed by providing stronger yet workable metals for teeth and sliders. Small changes in geometry and tolerances produced large gains in reliability. These improvements turned the device into a practical component for everyday garments and accessories. The design refinement process continued as new uses and materials emerged. As demand grew, manufacturing shifted from bespoke workshops to dedicated factories. The production of zipper components required dies for stamping, machines for weaving tapes, and specialized tooling for assembling sliders and stops. Quality control practices were introduced to minimize mismatches and faulty parts. Economies of scale reduced unit costs and made zippers affordable for mass-market clothing. Different factories developed variations suited to available equipment and local materials. Copper, brass, and later aluminum provided options for teeth that balanced corrosion resistance and strength. Textile makers developed tapes with consistent widths and weave patterns to accommodate assembly machinery. The supply chain became more organized, with separate firms often producing teeth, sliders, and tapes before final assembly. This industrial ecosystem supported wider adoption and allowed designers to specify zippers more confidently in product plans. Over time, global trade enabled patterns and standards to spread across regions. The basic mechanism of a zipper relies on three parts that work together: the teeth or coil, the slider, and the tape. Teeth come in several forms and are designed to engage with a complementary profile on the opposing side. Coil zippers use a threaded spiral of monofilament that interlocks when brought together. Molded plastic and stamped metal teeth use shaped profiles that lock when guided by the slider. The slider performs two tasks, depending on its motion. It brings the individual elements into alignment so they mesh, and it separates them when moved in the opposite direction. Inside the slider, a channel narrows or widens to press the teeth together or allow them to disengage. The tape is the flexible textile strip that carries the fastener and provides a surface for sewing into garments. The interaction among these parts determines smoothness, strength, and resistance to misalignment. Small differences in geometry or friction can noticeably change how a zipper behaves. Designers choose combinations of parts to meet the needs of a particular product. Various tooth materials and forms offer different trade-offs between durability and flexibility. Metal teeth are valued for strength and a certain tactile quality when moved, while plastic teeth reduce weight and resist corrosion. Coil designs allow greater flexibility along curved seams and are often quieter in operation. The choice of tooth spacing affects load distribution and ease of engagement. Larger teeth handle higher loads but add stiffness. Smaller teeth create a smoother overall profile. The slider material and finish influence friction and wear over time. Engineering considerations include coefficient of friction, hardness, and susceptibility to environmental factors such as moisture and salt. Sealed or water-resistant variants include additional coatings or protective tapes to limit ingress. Manufacturers often test materials under accelerated conditions to predict performance in real use. The selection process balances performance, cost, and intended application. The slider is a compact component that directs the joining and separation of elements. It contains a channel and wedge that apply lateral and vertical forces to the teeth as it moves. Basic sliders are simple, but more complex versions incorporate locking springs or pull tabs that improve user control. Locking sliders prevent unintended opening under tension, which is useful for pockets and luggage compartments. Some designs include two-way sliders that can close or open from either end, enabling adaptable access. Precision in the slider channel is critical to avoid misalignment and excessive wear. Manufacturing tolerances for sliders are often tighter than those for teeth because the slider experiences concentrated contact. Lubrication and surface treatments can improve long-term smoothness and reduce noise. Designers consider the expected number of cycles and environmental exposure when specifying slider types. The tape that supports the teeth is an important element that connects the fastener to flexible materials. Tape weave, thickness, and flexibility affect how the zipper integrates with garments and accessories. Heavier tapes provide more stability for high-stress uses, while lighter tapes reduce bulk in delicate textiles. Edge treatments and stitching techniques are selected to ensure the tape remains secure and does not fray. Industrial sewing practices and automated insertion machines rely on consistent tape dimensions. Tapes can be dyed to match garments or left neutral when hidden under flaps. For specialized uses, tapes may include coatings or laminates that increase water resistance. The interaction between tape and substrate influences comfort when zippers are used in clothing. Producers document tape specifications to ensure interchangeability between suppliers and assembly lines. Good tape design reduces failures that originate at the seam rather than within the fastener itself. As zippers became global commodities, standards organizations worked to define dimensions, test methods, and nomenclature. Standards help manufacturers and designers specify components that will fit together and perform consistently. They address topics such as tooth spacing, tape width, tensile strength, and corrosion resistance. Test procedures are described for cycle life, pull force, and environmental exposure, so results are comparable across laboratories. Standards also define marking and documentation practices that assist supply chain management. International cooperation allows patterns and specifications developed in one region to be applied elsewhere, reducing trade friction. Compliance with standards is often voluntary, but becomes de facto mandatory through buyer requirements and procurement contracts. Small and large producers alike consult these references when designing new products or validating alternative suppliers. The existence of shared standards simplifies communication and reduces costly mismatches during assembly. Testing and quality control are central to ensuring a zipper meets its expected life and safety criteria. Manufacturers subject assemblies to repeated opening and closing cycles to determine wear characteristics. They measure the force required to separate engaged teeth and monitor how this value changes over time. Environmental tests simulate humidity, salt spray, and temperature variation to evaluate corrosion and dimensional stability. Accelerated abrasion tests assess how teeth and tapes hold up to rubbing from fabric or other components. Failures are traced to specific causes, which may include improper heat treatments, dimensional drift, or incompatible coatings. Statistical process control methods are often applied in factories to detect trends before they produce defective lots. Certification and batch testing may be required for critical applications such as uniforms, protective equipment, and safety gear. Reliable testing reduces returns and helps manufacturers maintain consistent reputation in the market. Over time, designers adapted the basic zipper to diverse applications beyond everyday clothing. Sturdy metal zippers found use in heavy luggage and outdoor gear, where abrasion resistance and load capacity matter. Waterproof and sealed designs appear on technical garments and equipment that require barrier performance. Invisible zippers with narrow tapes are preferred in tailored garments to maintain a smooth silhouette. Two-way and separating zippers enable functional design in jackets, boots, and convertible items. Advances in polymer science allowed molded plastic teeth that are lighter and cheaper to produce, expanding use in cost-sensitive products. Specialty zippers include fire-resistant variants and decorative finishes for fashion applications. The evolution of the zipper reflects both technical innovation and changing consumer preferences. Designers choose from a broad set of options to balance appearance, function, and cost. This adaptability explains why a single mechanism persists across so many product categories. The history of the zipper is a record of incremental design, practical testing, and standardized practice. Each improvement in tooth geometry, slider function, or tape construction contributed to a more dependable component. Manufacturing advances and international standards supported wider use by reducing variability and uncertainty for designers and consumers. As materials and processes evolved, the range of applications widened to include technical, fashion, and industrial fields. The simple act of closing a seam now reflects decades of engineering choices and quality assurance practices. Small details, such as the finish on a slider or the weave of a tape, often determine user satisfaction and product longevity. The device remains largely unobtrusive, performing its role quietly while supporting many aspects of daily life. Thanks for joining us for History of Zippers, Design, Mechanism, and International Standards. If you are still awake, please stand by for our next program.